Hello, I'm Timothy Chase with the University at Buffalo Drones Lab, and this is our work on Mars, multi-view attention regularizations for patch-based feature recognition of space terrain. Spacecraft that maneuver within close proximity to planets, moons, and asteroids leverage the visual tracking of surface features, called landmarks, to perform terrain-relative navigation. The current state-of-the-art is traditional template matching and correlation techniques to landmarks that are crafted offline by human ground operators before any navigation can begin. This results in many deficits to the visual front end of the system, including increased mission timelines and costs, sparsity in the feature space, poor generalization, and poor runtimes. It would be more beneficial to detect and track these features at navigation time, similar to Earth-based algorithms such as Visual SLAM. Recently, new generations of onboard radiation-hardened inference accelerators have come to fruition, enabling in-situ and near real-time terrain detection methods. A robust description mechanism is still needed to close the loop, however. This objective is similar to many terrestrial tasks in image recognition, where current systems aggregate pre-trained foundation model features and are using high-parameter transformers coupled with multi-forward pass and re-ranking methods. This makes it hard to execute on current spacecraft flight processors that struggle with comparatively simple models such as the Inception and ResNet 50 class. Furthermore, space landmarks are more fine-grained than even the most demanding terrestrial datasets, and there is no room for large-scale dataset aggregation due to the sparsity of space imaging data in general. So how then can we develop a lightweight landmark description solution? We can begin by looking at metric learning, the foundational backbone to all terrestrial discriminative learning tasks. It is, however, challenging for metric learning alone to reason about the extreme levels of appearance change encountered during terrain-relative navigation. Examining the literature in rotation equivariance and spatial attention shows little improvement, as the focus of model attention is still disparate. We hypothesize that this difference in attention focus is the core of the issue, and we must therefore make the attention mechanism view-aware. This forms the basis of our proposed work, multi-view attention regularizations, or MARS. We start with a learning framework that augments single landmark instances into multiple views. And we learn a traditional metric learning objective for discriminative representation. We collect all intermediate attention maps from our encoder network and embed channel-wise attention information into a shared similarity space. Similarly, we embed both height and width spatial-wise attention information, and ultimately align the attention between multiple views through these additional soft similarity constraints. For evaluation, there are very few space imaging datasets at the time of presentation, and only one of patch-based landmarks. To better serve the research community on this difficult task, we introduced a Luna 1 dataset consisting of 5,000 lunar crater landmarks and 2,000 emulated navigation frames from real-world NASA data products. We leverage moon craters from Luna 1, as well as Mars craters and Earth stadium landmarks for experimentation. We compare 3 versions of models, including traditional convolutions with squeeze and excitation attention, rotation invariant convolutions with coordinate attention, and the addition of our Mars attention constraints. We evaluate 9 metric learning losses found recent in the literature, and perform a traditional and incremental recall at 1 experiment. For recall at 1, Mars shows impressive performance improvements, raising recognition accuracy for many metric learning losses on Earth stadium and moon crater landmarks, while retaining competitiveness against pure rotation invariance and coordinate attention on Mars crater. Overall, a Mars model variant is best in class for Earth stadium and moon crater, while incredibly similar to Mars crater. Similar results are seen for the incremental recall at 1 experiment, where a Mars model variant is best in class on all datasets. We additionally perform navigation-style experiments on the navigation frames from Luna 1. For landmark recognition during this navigation, the proxy anchor metric learning loss with Mars attention constraints performs the best. For an emulated kidnapped robot problem over the different orbits of the navigation frames, Mars retains competitive performance overall and improves many metric learning losses where rotational invariance and coordinate attention layers fail. Qualitatively, we demonstrate improved attention alignment with Mars, and showcase this alignment across each environment. We also see how Mars leads the convergence on challenging setups, compared with pure invariant and coordinate attention layers. During training, Mars improves stability by keeping attention similar, while also improving learning speed, promoting faster, more uniform convergence. Thank you. We hope you check out our paper for more details.